The title of our paper is Deep Video Inverse Tone Mapping Based on Temporal Clues. The authors are from Peking University. Because of the lack of high dynamic range video content, we need video inverse tone mapping methods to convert real-world low dynamic range videos to high dynamic range videos. First, we analyze the LDR video shooting process to capture the most important information from a scene. Cameras usually choose an appropriate exposure value based on the lighting conditions and the object. This exposure value changes make it possible that overexposed areas in current frame are normally exposed in other frames, providing valid information for recovering lost textures. We call this phenomenon temporal clues. Exposure changes tend to be designed very slow and smooth to ensure filmed video not flicker. This means temporal clues often far away from current overexposed frame. We want to leverage temporal clues to efficiently convert real-world LDR videos to HDR videos with fidelity and temporal consistency. The most straightforward idea to leverage temporal clues is using existing temporal models, such as repeating image ITM, sliding windows, or recurrent model. But these temporal models failed because repeating image ITM will cause temporal inconsistency. The small window size of sliding window-based models can reach far distant temporal clues, while a large one may lead to a significant increase in computational complexity, and in RNN-based models, temporal clues fade when long-term propagated. So, we propose a new temporal model which adopts a global sampling and local propagation strategy. First, globally sample some reference frames from the whole input sequence with a large stride. Because exposure changes are slow, it is very likely that sampled reference frames contain valid temporal clues, like orange frames in this figure, and then extract useful temporal clues from these reference frames to recover keyframes. Second, propagate information in reconstructed keyframes to their neighbors. According to the proposed temporal model, we design a two-stage video ITM pipeline. In the global sampling stage, as black arrows in the figure use ICAM to reconstruct keyframes. The ICAM is designed based on 5-level UNet, but a simple UNet cannot meet the requirements of extracting and aligning temporal clues. So, a local feature alignment block is added. It is composed of flow correction, deformable alignment, feature fusion. These three are used to solve the following problems: alignment of overexposed and normal exposed areas, large motion alignment due to global sampling, efficient feature fusion, and a global feature aggregation block composed of several swing transformer blocks is added to adjust global exposure. In the local propagation stage, rather than directly using ICAM to process all frames, FCPM chooses to propagate the information in the reconstructed keyframes to their local neighbor frames, which improves the overall efficiency. And the FCPM regard each frame in several adjacent groups of pictures. It is taken care by several reconstructed keyframes to ensure temporal consistency. Since there are few publicly available HDR video datasets, we propose a low-cost HDR video data synthesis method. It can utilize existing HDR image and LDR video datasets to synthesize diverse HDR video datasets. It uses inverse tone mapping and random warp to convert LDR videos and HDR images to HDR videos, and then degrades these HDR videos to obtain LDR-HDR video pairs. The above figure shows that image methods like HDR-CNN, differentiable HDR, single-DIR, and FMNet cannot restore textures from the real available temporal information. Sliding window method deep victim fail equal. Due to the lack of explicit exploit, temporal clues fade gradually when propagated. On the contrary, based on full use of temporal clues, the proposed method can generate impressive results with high fidelity. The below figure shows an example of a real-world LDR video shot by iPhone 13. The proposed method can reconstruct realistic and natural textures with the help of temporal clues in reference frame. It demonstrates the generalizability of our method for real-world cases. We evaluated the estimated HDR in terms of HDR-VDP3, which is a commonly used metric to measure the quality of single HDR image reconstruction, and HDR-VQM, which is designed for evaluating the quality of HDR videos. The results show our method outperform other methods on all 4 datasets. In summary, we analyze the temporal clues in LDR videos and propose a new temporal model with the global sampling and local propagation strategy and a 2-stage video ITM pipeline to efficiently convert real-world LDR videos to HDR videos with fidelity and temporal consistency. The proposed can exploit temporal clues effectively and recover overexposed areas with high fidelity efficiently, and we design an incremental clue aggregation module to align and fuse frames with exposure changes and large motions under ITM task. And we design an efficient feature and clue propagation module to propagate the reconstructed keyframes to their neighbors and generate temporally consistent results. And we propose a novel dataset synthesis method to obtain HDR video training dataset. Only using available HDR images and LDR video dataset, experiments demonstrate that the proposed method outperforms the state-of-the-art methods both on quantitative and visual quality.